In the networked robotics algorithms we've encountered so far, the robots have all been doing the same thing: move towards the center of mass of your neighbors, or move to some offset of that quantity. But what if we want the robots to do something else? For example, consider a building construction site where we have a robot carrying a hammer that has to be close to the robot carrying a set of nails. The robot carrying the set of nails wants to be close to the robot carrying planks of wood, which is helping a human to build something. But we don't want the robot carrying the nails to be too close to the human, because, well, nails can be dangerous. So how do we encode spatial requirements for a specific pair of robots? Weighted graphs, coming up next in this episode of Networked Robotics. Hi, I'm Chris, a robotics species student here at Georgia Tech. Let's take a look at a simple rendezvous problem, where we consider a team of 11 robots under the assumption of a delta disk graph. We will assume a carefully picked initial condition where we have most of the robots on the far left, one in the middle, and one on the far right. Let's see what happens. After a short amount of time, the robots become disconnected. Can you see why? The initial graph is connected, therefore the consensus equations should in theory work. However, because of our unbalanced initial conditions and the limited sensing of the robots, we see that the graph becomes disconnected. How can we solve this? We need to treat the neighbors differently. This means that the middle robot should place more importance on the far right robot, and the far right robot must hurry up in order to reach the middle robot and the rest of the robots on the left. How do we do this? We do this by adding weights to the edges of the graph.
The idea behind weighted graphs is to add a function to each edge of the graph that depends on some selected quantities relative to the nodes it is connected to. We call these functions edge weights. As a particular case, we could also have edges defined as constants. For example, in the case of nodes representing ground robots, the weight between them can be a scalar value that depends on the position of the two robots it's connected to. In order to denote the presence of weights in a graph, we expand the list of ingredients required to define a graph, and in addition to the list of nodes and edges, we now include a list of weights, one for each edge in the graph. With this definition in mind, we can include the weight corresponding to each edge of the graph in the consensus equation by multiplying each edge-wise term by its corresponding edge weight. In this way, we obtain the weighted consensus equation.
The next question that we want to answer is, how do we design the weights? The weights depend on the problem that we want to solve, and finding the right weights that describe our problem accurately is a bit of an art. However, there is one powerful way that people often use to solve this problem. Consider energies as our weights.
The idea of representing objectives or constraints through energies, sometimes referred to as virtual energies, is common to many fields, including robotics. For practical reasons, at least in the context of motion control of robots, it makes sense to think of the energy on a specific edge as a quantity that depends on the distance between the position of the two robots corresponding to its nodes. In addition, in order for a quantity to be an energy, there are two conditions it should meet. One, it should be a real valued quantity, always greater than or equal to 0. Second, it should be symmetric, meaning that the energy between two nodes I and j should be equal to the energy between j and I. If we associate an energy to each edge in the graph, the total energy of the graph can be computed as 1/2, because we don't want to count edges twice, times the sum of the energy between each node and its neighbors. Now that we have defined this energy, what should the robot do with respect to it? The second assumption we make, and this is the real reason for using energies, is that robots will move in such a way that the energy in the graph always decreases. The implication of imposing that robots are moving in the direction that depletes the energy from the graph are the following. Let's consider the particular case of the energy between robot I and one of its neighbors, let's say J. Since the energy associated to this edge must decrease, the velocity of the robot can be computed as the partial derivative of epsilon sub ij with respect to the position of I. We note two things. The first is that we are imposing this to be the velocity of the robots, and we explicitly show this by adding an exclamation mark on this equality. The second thing to note is that if you have never encountered partial derivatives, the idea here is simply to say that the robots should move in the direction that makes the energy decrease as fast as possible. Then, by expanding this partial derivative, we note that we can write the velocity of robot I as a scalar times the difference between the robot's positions themselves. Interestingly, this scalar is exactly what we called an edge weight at the beginning of this episode. In conclusion, if we repeat the same procedure for all edges robot I is connected to, we obtain the node-level weighted consensus equation, which corresponds to the gradient descent, our partial derivatives, on the energies of the graph. Pretty cool, right?
At first glance, this may seem like a lot of math. And you're thinking, what on earth does this have to do with Rendezvous and robots being disconnected? Well, let's see.
Let's start from this nice and friendly definition of energy. Remember, you can select this energy in whatever way you like, as long as it helps move the robots in the way that you need them to move. Well, if we compute the maximum direction of change of this function through our partial derivative, we obtain the expression on the right, which simplified leads simply to x sub I minus x sub j. Finally, by repeating the same process across all neighbors of robot I, we can write the weighted consensus form for the particular energy we considered, and voila, the old friend consensus equation.
It turns out that the entire time we were running this Rendezvous protocol, we were minimizing this special energy. As we will see, we can be very creative in designing these energies to allow us to do some pretty interesting things with our robots. Going back to the problem that we stated at the beginning of this episode, can using energies along the edges help us in designing strategies that allow us to ensure that robots that are close to being disconnected stay connected?
To answer this question, let's plot the progression of the edge energy as the distance between two generic robots, say I and j, changes. In the case of standard consensus equation, this energy is proportional to the square of the distance, and its progression looks like this. The reason why the robots in the experiment at the beginning of this episode got disconnected is that this energy is not strong enough to keep the robots from moving too far away. A possible remedy is to design an energy function that increases to infinity as the robots approach their threshold sensing radius delta. For example, let's consider the energy represented by the orange line. As we can see, as the distance between I and j approaches delta, the value of the energy goes to infinity. If we can find an expression for an energy that follows this progression, we can then compute the corresponding weights to keep the robots within distance delta. For example, an energy defined as the one over here increases to infinity as the distance between I and j approaches delta. By computing the partial derivative of this energy, you get the corresponding edge weight, W sub ij.
Now, let's run our example again, now using our specially crafted energy function that increases as our robots approach the threshold sensing radius delta. One can design energies to accomplish a number of different things. For example, one thing that you can do is you can assemble formations, which is going to be the topic of the next episode. Another interesting application of this idea is to design an energy that pushes away robots from getting too close to each other, thus achieving a collision avoidance effect. That's it for today's episode. Don't forget to like and subscribe, and check out our GitHub page for the Robotarium to check out the experiments for today's episode. Thanks for watching.